So,
Okay, so good afternoon, everybody. So I want to wrap up as soon as possible in the sense that what I'm going to do is I'm going to show you various slides which tell you how to use the Bosonization technique to calculate the dynamical correlation function of interacting Fermi systems. In fact, exactly. Okay, so that is the main advantage of this technique, which enables you to study the correlation functions exactly. But there is a caveat to this, and that is that it's exact only if only for systems where the number of right movers is conserved separately and the number of left movers is conserved separately. So as somebody asked me a very pertinent question last time, was that what about systems where you have what is called the backward scattering, where the number of right movers plus the number of left movers are conserved, but they are not separately conserved. So you can have a situation where right movers can get converted to left movers. So that's called backward scattering, and those are very important processes. For example, when you have impurities in your systems, that it leads to backward scattering generically. I mean, that is always the case. But you can also have backward scattering when you have very short range interactions, like hard sphere interaction. So backward scattering is just like two particles bouncing off each other. So the direction of their momentum changes. So a right moving particle becomes a left moving one. So if you disallow that, and if you only include what are called forward scattering, where the scattering between two particles only changes the magnitude of the momentum, but not the direction. Because after all, in one dimension, you can only have two directions, right or left. So if you have scattering which only changes the magnitude of the momentum, but not the direction, that's called forward scattering. So when you have only forward scattering in your problem, that such a problem is exactly solvable by bosonization. And that's the main attraction of this technique. Okay, so let me, instead of just giving you preamble all the time, so let me start with the, so I'm presenting something as you can see. Okay, so can you see?
sir.
Can you see this diagonalization of the Bosonized Hamiltonian?
Yes, sir. Yes.
So if you remember that we stopped somewhere here, isn't it? Can you remind me? Is that so? This is basically the Bosonized form of the kinetic energy. So remember, I described all this, that you can write the when you have forward scattering between fermions, right? You remember all this, isn't it? I just want you to confirm that I've done whatever was before this. Do you remember all this? Do you remember this term? I remember some of it. Just stop me, man, if you feel like you don't remember. Do you remember these slides? There was a right mover interaction. You have right, left. I remember all this.
Yeah. Yes, sir.
So I'm going to start here. So the Bosonized form, in any case, I know it's a lot of information and it's difficult to swallow all of it in one go. So I'm going to, convert my entire notes into PDF, and I'll be sending to all of you and also uploading on my website. So you can refer to it anytime you want. And that's one of the purposes of this series. It's just to, it has archival value. I want it out there so that, and I also want it to be correct in the sense that that's exactly why, you know, I have been sending messages to Professor Haldane, who has been really nice to reply to me nicely, and he's explained so many details which I didn't know. And what is even more frustrating is that I didn't know because probably I am not clever enough. But it appears that much of this is not so well known to people who ought to know better. Because if they knew, they could easily have pointed out some reference where I can find it. And it's not for want of trying. We have tried a lot, and there is no proper reference that explains much of this, as well as both Professor Alden and I together succeeded in doing. So that's the reason why I feel that this series of lectures is important. Okay, so the bosonized form of the uh, interacting Hamiltonian, so you see, can be written in this fashion, and this is the eigenvalue of the normal ordered momentum times the Fermi velocity, and these are the deviations from that, you know, the ground state value. There is the Virasoro primary state value of the right moving kinetic energy. And then you have, when you have interactions, the bosonized form of the, when you write it in the bosonized form, the Fermi velocity gets shifted. Basically, it acquires certain modifications as a result of the interactions. So you can have interactions where we purposely write it differently. You know, if you have, well, provisional, you know, if you to take the interaction term very literally, then VQ and WQ are the same. But this method allows for it to be different if you wish to, for it to be different. Okay. So, so the point is, how do you diagonalize this? So notice that there is no, I mean, the bosons being particle hole operators, there's no expectation that it will be conserved or anything. There's no requirement for it to be conserved, so that you have two annihilation, two creation, etc. So now how do you diagonalize this? So you say that, look, we claim that it's going to be diagonalized in this fashion because, you know, there are two species R and L. So when you diagonalize, you should still have two species 1 and 2. And you write the diagonal form of the operators as linear combinations of the original operators. So this is how it's going to look like, and these are just numbers, and this is just an identity. If you take DQ1 commutator with B dagger QR, you get an identity. You take DQ1 commutator B minus QL, you get an identity, etc., etc. And there all the other commutators are 0. Okay, so now you just what you do is you take the you successively take commutator of this H with D1. So when you take with D1, then this D1 and D2 are independent. So you get a D1 commutator H is omega Q1 D1, right? And well, the NR, remember that the N's commute with all the bosons. So that this is just a number as far as the N's are concerned. I mean, as far as the bosons are concerned. So now, so when you take commutator, you end up with this result, because, you know, so there are two versions of this. There's the diagonalized version and the undiagonalized version. So if we take commutator on both sides with respect to dq1 and equate both of them, and this is what you get. And similarly for dq2, this is what you get. And then now you see dq1 is now some complicated linear combination of the B's and B daggers, but this linear combination had better be precisely this one, because we had that is the requirement that the D's have to be that linear combination. So then you equate that, you force this linear combination to be the same as this linear combination, and when you do that, you get these relations between those coefficients. These commutators are numbers, okay, and these numbers obey these consistency conditions. So now when you do that, you see that this omega has, remember that you have to also make sure that the limit, of course, plus or minus, if we ignore the minus root, because when you take VQ equals WQ equals 0, you should get back the non-interacting theory. Remember what that is, and that is if all the interactions are 0, there's nothing here, there's just VF. So it's VFQ everywhere. So it's plus VFQ for R and plus VFQ for L, but remember there's a minus Q there, so the operator has a minus Q, so that's why that takes care of the left part of it. So, but the coefficients still are VFQ, okay? So that's the reason why in the interacting theory we choose both as positive square roots, but mathematically you get the other sign, we ignore that. Because when you put WQ equals VQ equals 0, you should get back VF mod Q in both the cases, right? And so that's Q is greater than 0. So, so that's why I've dropped that subscript 1 and 2 because they're the same. And then so you get an explicit, so then you can equate these two and call it C1, equate these two, call it C2. And then you'll see that all these coefficient commutators, which are numbers, can be written in terms of these new complex numbers when there are fewer of them. The idea is that you are successively simplifying the problem by expressing the commutator in terms of fewer and fewer unknowns. So now you have CQ1 and CQ2. So now how do you find these? It's easy that so when you re-express that linear correspondence of the D's in terms of the B's, so this is what it is in terms of these new unknowns, C1 and C2. So how do you find them? You find them by imposing the condition that the D's are canonical bosons. In other words, their commutator with its adjoint should be exactly 1, and they should commute across species and that sort of thing. So when you enforce those conditions, you get Q1 to be this, CQ1 to be that, and similarly CQ to be, well, I haven't written down what that is, CQ2, you can work it out yourself. It's exactly the same, isn't it? Because, yeah, CQ2 will be the same because, yeah, it's the same, everything is same, yeah. Yeah, so CQ1 equals CQ2 equals this, okay? So the only thing is that D is related to BQ here, this becomes minus, this becomes del. So otherwise they're the same. So CQ1 equals CQ2. As you can impose the condition, you get back the same thing. So this is equal to CQ2 also. Okay, so that completes the correspondence. So you can do the inverse also. You can express the B's in terms of D's, which is also important. I'm going to use that because finally the D's are the ones that diagonalize your interacting theory, the D operators. The B's are the original bosons. So, so remember that now as promised, I'm going to start evaluating the correlation functions of interacting theories. And first, in order to do that, first you write down the right moving density in this fashion. And then what I'm interested in doing is finding the correlation function of the sort. We are, of course, also interested in, remember that the right movers and left movers interact with each other through two-body interactions. So this is also going to be non-zero. Okay. So RL is not going to be non-zero. And based upon this definition, it's clear that these correlation functions, which can be evaluated exactly, that's the attraction of this technique. And these correlation functions can, of course, be expressed in terms of the correlations of the B's and B daggers. Okay, so now the question is, how would you find that? So you find that by expressing the B's in terms of D's rather than, remember that we express the D's in terms of the B's, so you just have to invert it. So the inversion is equally simple, it's this. Okay, so you can verify this is also an identity. Take the commutator of both sides of this equation with the DQ1 dagger, you get an identity. Similarly, take commutator of this equation with DQ2, you get an identity, etc., etc. And remember that these coefficients have already been evaluated earlier. Okay, they've fully been evaluated in terms of the interaction strengths and so on and so forth. So now, when you express these correlation functions, you end up getting nice exact expressions, and that's what they are. Okay, so these are the final answer when you are interacting fermions. So this is for the B, this interaction, and all other ones are zero. Well, LL is also non-zero, by the way. Okay, I haven't written that down. Okay, yeah, that's implied, right? Okay. So yeah, so that is so I've reached this far where I'm just telling you that look, if you wish to, you can go ahead and calculate many of the interesting properties of interacting fermions. But remember that I had a nagging suspicion about the formalism itself. That's what I've been complaining about to Professor Haldane for ages, and that because this formalism is so incredible that you can map a theory of interacting fermions to non-interacting bosons. Basically, the very fact that you can map a theory of fermions to bosons, exact bosons, is quite incredible to me. And every time I think about it, I feel, well, there has to be something wrong here. And because my suspicions are also compounded by the fact that rigorous at least the questions that I want answered don't have ready proofs anywhere, and which is why I was forced to ask Professor Haldane so many times. And he also agrees that the questions I have asked are very pertinent, and they should have been asked and answered a long time ago explicitly in writing by somebody who's writing a review article. Unfortunately, nobody ever does that. Okay, so that's the reason why I'm giving these lectures, so that once and for all those questions are first asked, and I'm going to explain to you why those questions are important, and then I'm going to answer them. Okay, so what is this question? One of the central claims of Bosonization is that these two are the same operators, right? And remember what the B's are. The B's are just a combination of C dagger and C, and the N is just another combination of C dagger and C. So this is a remarkable claim that you have a operator that's expressed in terms of product of two C's, and it's the same, exactly the same operator when you express in the product of two B's and the square of N's. But then the product of two B's involve four C's. That means two C daggers and two C's. But this only involves one C dagger and one C. So it's incredibly hard to believe this unless somebody actually proves it. So like I told you that one of the, most of the books, if at all they make an effort to prove this, they kind of get away by just convincing you that, you take this operator, take the commutator with BQ, it's the same on both. That's very easy to show actually. If you take the commutator with the B's, it's very easy to show that these two are the same commutator. But that's not good enough, because you have to show that this commutes with any other operator the same way. If these two are exactly the same operator, whatever you do to this operator, you should get back the same thing when you do it with this operator. So in particular, if you take just the annihilation operator CPR and take the commutator with PR, you should get back whatever you get from here. And that is a question that's important and extremely important according to me, and it should have been proved explicitly and included in some notes, some book. It has never been done, and which is why I asked this question. And I'm characteristically provocative in the sense that I kind of, when I write, I say that I don't believe this, and I send it to people just to provoke them into giving me an answer. Because if I'm ambivalent, they say, okay, go and figure it out yourself. But so if I say I don't believe you, then they'll go on the defensive and they'll feel that it's their obligation to prove it. So that's fortunately in this case, my strategy has worked. So I sent out a mail to him saying, I don't believe this. So he was nice enough to send me a proof, which is what I'm presenting right now. Okay, so the question is the following: show that if you take the commutator of the normal ordered momentum with Cp, you get the same answer. So that means this commutator is the same as this. This is obvious because you see, when you express in terms of the fermions, you take Cp commutator with this, you get clearly P there, if P is positive, for example. So we'll assume P is positive without loss of generality, because you can always do the other thing later on. So, so the point is that you have to show these two are equal, else I don't believe anything. So how do you show these two are equal? So when I take the commutator of this horrendous, 4 fermion version of the Hamiltonian, I end up getting this result. Now, how do I show that this is same as P times the fermion? So to do that, well, strictly speaking, then I have to show that if I divide by P, it is basically going to anti-commute with other CPs and other CP daggers like that. But the very general proof, I won't do it. But all I'm going to show is that CP dagger plus okay, if I do this, I pre-multiply by the CPR dagger and post-multiply by CPR dagger, and I add these two. What will the left-hand side become, given that the C's are the fermions? So if I add these two, what can I expect on the left side? Are you listening to me? Can you hear me? What do you expect when so what I've done is I've taken this, you know, putative identity. I mean, like, this is what I want to prove, that I want to show that this is an identity. So if this is an identity, then I should be able to pre-multiply by C dagger PR or post-multiply by C dagger PR, and they should still be identities. And if they are, I should be able to add them and they're still identities. So in other words, whatever I do, this should be an identity. So if I pre-multiply by C dagger PR, post-multiply by is the same, and I add, what happens to the left side? What do I get on the left side? I think unless somebody says something, I'm going to assume you can't hear me, because
Yeah, sir. So the left
so the
will
left
get
will get
P.
P. Right, you get
Yeah.
P because it's the anti-commutator of C dagger, and see, that's the definition of anti-commutator, isn't it? C dagger, C plus C dagger. If you add these two on the left, you get anti-commutator of C dagger, which is 1, because these are the same P's and I mean, both are right movers. So the left side is going to be a P, and when I add these two, it's going to become like this. So you can work this out. See, a lot of this is little bit tedious algebra, and I have given all the steps so that you don't have to necessarily follow everything I'm saying while I'm giving this lecture. So you can just take comfort in the fact that it's out there, it's already been typed up. So you can always, sit at leisure and verify all the steps on your own. So that's the advantage of typing out everything. It takes effort, but it's worth it, because like I said, somebody wants to verify, they don't have to scratch their head, ask some Professor Haldane, who may get irritated if people like me keep asking him. So the whole idea is that once this is out there, so people can read this instead of asking him or somebody else. Okay, so when you add these two, you get this, which you can verify on your own. So now I have to show that this whole mess is equal to just a number. So that means it's just proportional to the identity operator, which is quite a remarkable and not at all obvious statement, because after all, what is this commutator? It's just another proportional to some fermion. Or in particular, it's going to be proportional to an creation fermion. So this is I'll tell you what it is. So it's going to be this. It's going to, so once you write it out, it's going to, so what you have to finally show that this is an identity. This is not at all obvious, okay? So, I mean, it's obvious in hindsight, but hindsight is, like they say, hindsight is 20/20. So there's a whole bunch of steps. So you just have to keep in mind. So this proof very crucially involves, as Nikhil Dani pointed out yesterday when he was going through these proofs, that it very crucially involves this the way we have constructed the fermions, where the p's are odd multiples of pi by L. So the anti-periodicity is crucial here. The p's are odd multiples of pi by L, but the q's are even multiples of pi by L. So p plus q are odd multiples of pi by L. So that's fine, but so it explicitly makes use of this idea. Otherwise, if you don't make use of it, you get a contradiction, and which is why I typed up that contradiction and sent to Professor Haldane saying, look, it doesn't work. So he had to scratch his head, fix it, and send it to me, implying that it's not out there so readily, because every time I ask him a question, he actually takes the trouble of typing up the proof rather than referring me to some paper or some book. It's much easier for him to do that if it's there. The very fact that he's not done that means it's not there. Otherwise, why would he take the trouble of... I'm going to display you the notes he sent me, okay? They're quite substantial. And it's so by implication, they're not there at all. So we are learning it from the first time from the expert himself. Okay, so the question is, how would you prove this? So you prove this by the following algebraic manipulation. So what you do is that you write p minus q as minus p dash. So this summation becomes this now, okay? And similarly, you write p plus q as p dash. So then the summation becomes like this, and this you split up like this. And then when you rearrange the terms, you get this and this and this and this, okay? So this is same as this. I mean, this is a duplication. Sorry, I should delete this. This is same. These two are same. Yeah. So what is different is this one. So what I've done is that so I have so remember, this is less than p. So I have included less than or equal to p and subtracted the term which is equal to p. So when I subtract, then this will become minus, because it gets subtracted by 2 pi by L, gets subtracted from this. So if this becomes plus pi by L, becomes minus pi by L. Now when you combine these two, clearly again, because these are fermions, C dagger plus C dagger C is 1. So this whole thing put together is minus pi by L. So that's very critical. So now, so what's going to happen is that you will get this minus pi by L in the middle, and then you get these two terms. Now, what are these two terms? You see, this interval is precisely this interval. This is the same thing in the reverse order. See, here p dash is greater than 0. Here also p dash is greater than 0. P dash here is less than or equal to p. Here also p dash is less than or equal to p. So these intervals are precisely the same. And this is so 2 pi by L. This is also 2 pi by L. Except now this is p dash, p dash, p dash, p dash, r, right more, right more. So now the only difference is C dagger and C dagger C, and there's a plus sign on both. So when you put them together, what do you get? You get C dagger plus C dagger C, which is what? What is C dagger plus C dagger C? And you combine these two. Is there a lag between when I say something and when you hear it?
It is 1.
It's 1. So therefore, when you put these things together, you get 2 pi by L summed over all the P dash in this interval minus pi by L. This is very critical. This is what I had missed earlier. And that's the reason why I thought it doesn't work. It does work. Okay. So remember that now we crucially make use of the idea that the P's are odd multiples of pi by L. So now P can be written as 2np plus 1 by times pi by L, and this is n dash. So in other words, you are summing over n dash, and remember that P dash has to be greater than 0. So you should start from 0, n dash equals 0. So that means P dash is pi by L. If you start from n dash minus 1, then P dash will become negative. That's not allowed. So you should start with P dash positive. So positive P dash means n dash starts from 0. So it starts from 0, which is pi by L, then you get 3 pi by L, etc., etc., etc. And then you have to stop once you reach P, which is, so in other words, you should, so n dash is getting summed over from 0, 1, 2, 3, all the way up to np, including np. Okay. So it starts from 0, including 0, and ends with np, including np. So how many such terms are there? So if you start from 0, including 0, and end with np, including np, how many terms are you counting? Because that's how many terms there are here. So you're adding 2 pi by L that many times. So how many times are you adding 2 pi by L to itself?
np plus 1.
Right. So that's exactly what you're doing. You're adding 2 pi by L plus 2 pi by L to plus 2 pi by L. However many P dash there are in this interval. And there are np plus 1 P dash in that interval. So that's 2 pi by L times np plus 1, and never forget this one. And then when you combine this, miraculously the same as P because of this identity and this definition. Okay. So as a result, this the original claim is, well, you can, it's not really, the proof is complete in the sense that the hardest part of the proof is complete. The easier parts involve showing the anti-commutation when P dash is not equal to P. That's easier to do. Okay. I mean, P dash is not equal to P, the anti-commutator is 0 rather than, you know, that's easier to do. So the hardest part is done. So if assuming you can fill in the rest of the blanks, then it's really remarkable that an operator written in this fashion is exactly mathematically the same as this operator, where the B's are the exact bosons. See, the fact that these are exact bosons is another miracle. That's called chiral anomaly. So remember, we proved that also in the beginning. So that's the starting point of this. So it's a series of incredible claims which require proofs. And that's the reason why I'm giving them, because nothing is obvious here. So you start with chiral anomaly, prove these are bosons. Then you have to also show that these are the same operators. Okay, we are not done yet. So there's more to go. Okay, so that is the as far as that central claim is concerned, that is it. So now what I'm going to do is I'm going to display to you the I'm going to display the proofs sent by Professor Haldane. Okay, so I've been like promising you that for ages now. And the reason why I want to do that is twofold. One is, of course, to give proper credit to the person who firstly invented this subject and finally took the trouble of explaining it to me for the first time properly. So there is that, acknowledging the originators is important. The other reason is I'm too lazy to type up in PPT format whatever he has typed up, which is a lot. Okay. So this is what he sent me on August 9, 2019. So this is like many versions refinements, because I kept asking him some questions. Joy and I kept asking him questions. I didn't get this, I didn't get that. So he had to keep answering and updating his file. So this is precisely what that is. So I have okay. So the idea is that so far, remember that we have expressed the operators such as density, which conserves the number of right movers in terms of the bosons. But what is even more remarkable and nearly impossible to believe is that you can actually express just the annihilation or the creation of the fermion, just this much, just the creation operator itself in terms of the bosons. I mean, that is at the outset absurd, because the bosons conserve the number of right movers, and this clearly does not. But then there is another operator which actually all it does, it just changes the total number of uh, fermions in the system without changing the state. Okay, so that's called the shift operator. So the shift operator together with the bosons are enough to express the fermion creation in terms of those two. So that is a remarkable claim which can be proven rigorously. And that is something that I have had trouble believing also. And but it turns out that it's true, and none of it, like I said, is obvious. So for a, remember that we are living on a circle. So there's a periodic delta function. This is the ordinary Dirac delta function. So this is the anti-periodic Dirac delta function. So this is the ordinary Dirac delta function put together. This is called the anti-periodic Dirac delta function. So when you have anti-periodicity, you can express like this. So if you take x to x plus L, you get back same thing with a minus sign. Okay, so this is how you write the anti-periodic Dirac delta function in terms of the, this is the ordinary Dirac delta function. Can you see my cursor highlights? Are you
Yes, sir.
okay,
Yeah.
good. So fine. So you see, the like I said, that when you're dealing with real space, the momentum space was very clean, isn't it? Because it doesn't have all these issues of cutoffs and so on. But the real space is nasty, because you see, when you have anti-commutator of CP and CP dagger, CP dash dagger, you know, the fermion in momentum space, when you take anti-commutator, you get Kronecker delta P comma P dash, right? So there's nothing, say Dirac delta is a nasty object because it's very singular and it's one of those so-called generalized functions. It's not an ordinary function. But whereas a Kronecker delta is very simple and innocent because it's either 0 or 1. So momentum space versions are nice to mathematically to handle. But unfortunately, not all calculations can be easily done in momentum space. Well, although I have a very nice theorem I have published in my first paper on the subject in 1998, when I was a PhD student in Illinois, where I showed how these bosonization ideas can still be made to work in momentum space. So there is a theorem involving, implicit function, how to write, if you have a function of a function in the position space, how to rewrite that in momentum space equally easily. Okay, I won't go into that, but point is that when you're dealing with real space, you're forced to do this because there's an implication that there's a cutoff there, because if you don't put in this, then you won't get these delta functions. So they remember that delta functions are actually limits of sequences of ordinary functions. So this limit, by implication that this limit achieves that same purpose. It gives you a sequence of functions, when you take this and anti-commute with its conjugate, instead of getting the Dirac delta function immediately, what you get is something which depends on epsilon, which successively becomes like the Dirac delta function as epsilon goes to 0. So now you see. So on the one hand, this superscript f refers to the fermionic version of the. So the implication is that you can rewrite this in terms of the B's and B daggers also. So when we rewrite this same operator in terms of the B's and B's daggers, that will have a subscript called small letter b. That means the bosonized version of the fermion. So this is the original version of the fermion. So which is the f. So the subscript f means the original version in terms of the C's themselves. Okay. So clearly, in terms of the C's, so when you have this cutoff, then it's going to look like this. And when you make epsilon goes to 0, you recover your Dirac delta functions. So this is already something I've explained. So the new ingredient is this operator, which is called the shift operator. So there is a Hermitian operator called theta r, which makes e raised to I theta r unitary. So if you put n equal to 1, so what this does is it creates from the Virasoro primary state containing the no fermions. So when nr is 0, it creates a state with nr equal to 1. So basically, it creates the Virasoro primary state with nr equal to 1. So all it does is it maps one Virasoro primary state to another Virasoro primary state. So from nr equal to 0 to nr equal to 1. So remember that Q's are positive, so they are going to look like this. And so now the goal is what? We have to express the ambitious claim was that you can express the fermion itself in terms of the bosons and this shift operator e raised to I theta, which is unitary. So then, in order to do that, we first recall the definition of B's in terms of the fermions, and recall that they annihilate the Virasoro primary state, and they obey chiral anomaly, etc., etc., etc. So now the claim is that this operator, right? This operator is precisely the same as this operator. Looks horrendously complicated. Everything is an exponent. So remember that this phi plus is the Hermitian adjoint of phi minus, and phi minus is defined like this, okay, in terms of the bosons. And this is that NR operator, normal ordered number of right movers. So you see, everything is in the exponent. The B's are all in the exponent, and this is your shift operator. And the claim is that these two are the same. Okay. So this is something that if x and x dash are not the same, it's kind of not you don't have to involve epsilon and be very fussy about it, because you can actually show when that epsilon becomes unimportant, because after all they add it's some additional term beyond x minus x prime gets added to some epsilon. But if x is not equal to epsilon, x is not equal to x dash, since epsilon finally tends to 0, you might as well ignore that right from the start. So when x is not equal to x dash, it's relatively easy without much fuss to prove this. So that's exactly what he has done. So he has evaluated, so this is called the bosonized version. So the annihilation operator can be written in this very complicated bosonic form. So when you rewrite that in terms of, so when you rewrite it that way, it's not at all obvious that such identities are going to be obeyed. So we'll have to actually prove it. So in order to prove this, first you do this, and then you show that this is the same as this, and then you evaluate the one with the order interchanged, and you get this trigonometric function with reversed argument. This continues to be the same, and then because these are normal ordered, okay, so this actually goes to 1. So in other words, that these are the same. So finally, look, it doesn't matter what it goes to. The point is, it's finite because these are finite operators. See, this is uh, what to say? Yeah, it's not some. Assuming this is finite, we have to actually show that later on. Okay, so let's assume this is finite as x tends to x dash, because we have to prove that finally. So if x tends to x dash is finite, then clearly if you add these two, you get 0, because this is x minus x dash trigonometric, then x dash minus x, but sine function is odd. So there's a sine chain, these are the same, and then 0 gets multiplied to this. So it is 0 unless this is something funny as happening here as x tends to x dash. But we'll later convince ourselves nothing funny happens as x tends to x dash. So as a result, this thing is 0 when x is not equal to x dash. So even otherwise, you have to show that, okay, see, when you add these two, it should be 0 regardless of whether x is close to x dash or not. So in other words, you have to show that this is always finite. So if this is always finite, then this is always correct. Okay. So let's keep that at the back of our mind. So this proof is incomplete unless you show that this is always finite. This operator there is no state in which the matrix elements of this diverge. Okay. So, so in that case, if that's finite, this makes sense. But then remember that we are not satisfied by this, because we have to show what happens as x tends to x. It should give you a Dirac delta function, isn't it? Because when x is not equal to x dash, fine. But what if x is equal to x dash? This should actually give you delta 0. So in other words, it should, strictly speaking, you should not show that this is equal to 0. You should show it's equal to Dirac delta. So how are you going to do that? So then you have to bring back these epsilons, because remember the Dirac delta functions are actually, when you introduce the epsilons, that's where they come from. So you have to carefully reinsert your Dirac delta functions. And my main grouse, which I have explained in my book, was that all the review articles and books that I have read, kind of even this Guillemard's book, they kind of implicitly put epsilon dash equals epsilon. You see, remember that there is an epsilon right here. See, these kinds of doubts will occur only in your head if you're kind of thinking about this day and night, and you're bothered by it. And uh, most people don't care one way or the other. So remember that here you are supposed to, he forgot to copy paste that here also. I mean, you have to remember that this does not involve epsilon. So you have to actually take epsilon tends to 0 first. So the idea is that this fermion anti-commutes with other fermions only after taking this limit. Otherwise, there is no, these are not fermions at all. It's some horrible, I mean, there is no implication that it's fermion. No, this is fermion, but the, this is strictly a Fourier transform only if this is 1. So this is going to be 1 only if epsilon tends to 0. So question is that you are supposed to take epsilon tends to 0. But unfortunately, in all the articles that I have seen, epsilon dash is equated to epsilon before taking that limit. That seemed very highly suspicious to me, because after all, this is a fermion in its own right. I mean, you're first supposed to take epsilon tends to 0 here, make this a fermion, take epsilon dash tends to 0, make this a creation fermion, then you take the anti-commutation, you should get a Dirac delta function. But rather what people do in the literature is that if you set epsilon dash equals epsilon, then immediately this is clearly going to, when epsilon dash, suppose you set epsilon dash equals epsilon, then as epsilon tends to 0, this is clearly a Dirac delta function which you, at x equal to x prime, you can easily work out. Actually, it's going to be the anti-periodic Dirac delta function, but you get the point, right? So, so if epsilon dash and epsilon are same, it is obvious that immediately x dash will tend to x, and this thing will go away, this thing will go away, and then you get one delta on the right side, anti-periodic delta on the right side, and this is the correct anti-commutation. So people kind of hurriedly, subconsciously set epsilon equals dash equals epsilon, and then prove this, and then they, dust their hands and walk away. But I was not happy. I said that how can you set epsilon dash equals epsilon? That nowhere it says, because these two don't talk to each other. You are first supposed to make epsilon go to 0 and make it a fermion, then make it anti-commute with another fermion after making its epsilon go away, right? So now when you do that, it's not at all obvious that that is how it is. But then to me at least, I don't know if it's not at all obvious to the rest of you, but it's not obvious to me. So you see, it is again, uh, it rests on the idea that this is normal ordered. So what will happen is that this will only involve the annihilation operators, and this only involves the creation operators. So when this happens, okay, so you can make epsilon go to 0 first, then you get something which is not a Dirac delta function at all, because there still is an epsilon dash there. So then neither is this going to be an identity for that reason. So now you make first epsilon goes to 0 first. Then you get something which is neither here nor there. Then you finally make epsilon dash also go to 0. Then you see, so long as this doesn't blow up, then the claim that if this is finite, then you are multiplying something which is finite. So it's the something finite times the antiperiodic delta function. But that something finite can easily be shown to be 1, because then you see first epsilon has gone away, and then epsilon dash also goes away, and by that time x dash has become equal to x. So this is going to be, so long as it is finite, it's also equal to 1. But then the question is, how do you show it's finite? So it's finite because it's normal order. So that's the point I missed actually. So you have to write it in a normal ordered form. Then if you write it in a normal ordered form, then you can show that it's because the normal order means that basically this is annihilated by the Virasoro primary state. So strictly speaking, remember what we have been doing for chiral anomaly. How did we prove it? So you have to show that this anti-commutator is proportional to the identity. So what you have to strictly show is that this commutes with all the fermions. So that means it is basically proportional to the identity operator. So it's a lot of hard work. If you want to do it properly, it's a lot of hard work. So instead of just appealing to your intuition, or pleading with the reader to use this imagination, or whatever it is, or just beg the equation, please work out, don't give me anomalies, don't give me funny things. So instead of doing all that, if you want to be strictly rigorous, all you have to do, so what do we have to do? We have to show that this is proportional to the identity operator. So strictly go ahead and take the commutator of this with the fermion, that's ck, then take the commutator with c dagger k. So you show that both of them are 0. So if both are 0, that means this is proportional to the identity operator. So if it's proportional to the identity operator, the proportionality is just its expectation value with the restore of primary state, which is immediately because this is annihilation, this is creation, that's clearly 1 already. Okay, so then it's very easy because once you show that this is 1, then the rest of it is just periodic, anti-periodic Dirac delta. So the hard work is actually to show that this operator commutes with all the fermions, both creation and annihilation. I haven't done that, but I can believe it. And those steps are missing here. So there is some kind of appeal to somebody's sense of please believe me type of thing. But I mean, it's believable to me now. I believe it. Earlier, I didn't believe it, but now I believe it. I haven't actually. So think of this as a challenge. Show that this object commutes with all the fermions, because this is it's a well posed mathematical question, because the 5 pluses are in terms of the bosons, which are in terms of the in term just products of C dagger and C. So the C dagger C sitting in the exponents here. So you know how to find the commutator of that with the fermions. So strictly speaking, it should not be difficult. Well, it should not be impossible. It's going to be difficult. It's not impossible. Okay, so assuming you can do all that, then the rest of it is easier. So this part is easier. You exchange, you get back. This is easy. Okay, this is easy to believe. All right. So now, well, then Professor Haldane has done a lot more also. He has shown this was fermions on a ring. He showed how to take thermodynamic limit. So that means that L tends to infinity. So taking thermodynamic limits requires some further subtleties, which I won't go into, because so long as it works for on a ring, I am satisfied. Okay. All right. So the next thing which he sent was that this was also sent on the very next day. So this was basically I said that all that is fine, but then you see what you have proved is just that if you take the anti-commutator of the bosonized version with other bosonized version, that means you take the anti-commutator of what is that? You take this one and anti-commute with itself, or like with its conjugate, then you get Dirac delta and 0, etc., etc. That okay, that's what this document does. That's fine. Well, that's fine, provided you work out those, that show that e raised to I, that thing is basically proportional to identity, and therefore it's equal to its expectation value, that sort of thing. So that's all fine. But I said that I still don't believe you unless you show that this way of writing psi anti-commutes properly with the original way of writing psi, which is this one. See, this is the original way of writing psi. So you have to show that the original way of writing psi anti-commutes with this way of writing psi, and this is a question nobody had thought of asking. And I said, I don't believe you until you show me that. So he was almost annoyed with me because I asked him this question. But finally, he proved it himself. Yes. Okay. So, and the proof is somewhat lengthy. Okay. So the proof involves writing. So this is how the original fermion version. First you prove the shift operator behaves this way with the fermions, and then you write the boson version with the epsilon there, and then you find its anti-commutation. So this is the bosonic way of writing psi. This is the original fermionic way of writing psi. So you have to show the anti-commutator of this with this should be Dirac delta function as usual. It's not at all easy to prove this, by the way. But it's a brilliant question, even if I say so myself, because it's an important question to ask. Nobody has asked it. And similarly, you have to show this is equal to 0. So there's a lot of steps which he was very kind enough to send me all the details, so you can work it out. You can find it out yourself. Okay. So as usual, you have to show that the rest of it. You have to show that this. So it's so finally he shows that this object is periodic delta function times something, and that's something. This is this whole mess which is arranged like this. So you have to show that this is 1. So the way to show this 1 is first you show that it basically it commutes with all the fermions. Okay. If it commutes with both creation and annihilation, fermion is proportional to identity. If it's proportional to identity, the value of this operator is its expectation value times identity. So the expectation value of this with respect to Virasoro primary state is 1. That's easy to verify. What is hard to verify is that show that this is proportional to the identity operator, because this is very complicated. This phi r is linear combination of the bosons with a shift operator, which is not at all easy. So this is the original fermion creation in the Fermi language, which is the Fourier transform of C dagger. And then again, this is also linear combination of boson in the exponent. So this horrendous mess is just one identity operator. Can you believe that? So you have to actually prove this. So that means to prove this, first you have to show that this operator commutes with all the fermions, both creation and annihilation. Therefore, its value is the expectation value with respect to Virasoro primary state, and because this is the identity, so this is proved. So then, if you do all that, you can convince yourself that the bosonized version of the Fermi field properly anti-commutes with the original version of the fermion, which was another important piece of the proof that was missing from the literature. Okay. So that's pretty much it. So, but then he has not stopped there. He has gone on to say, well, what if you have fermions with spin up and down? So then you have something called the Klein factor. So that in addition to the shift operator, you also have another thing which is called the Klein factor, where you have to show that well, even for a single spin, right and left, how do you show that the right mover anti-commutes with the left mover? Isn't it? Because this was only for one species, for the right movers only. This whole machinery is just for the right movers. So you remember that you can write the right moving boson, right moving fermion in terms of the right moving B daggers, and this is a right moving shift operator. So if you have another species called left mover, then the right mover and left mover have to anti-commute, because if you just don't include any additional ingredient, they will actually commute instead of anti-commute, because you see the theta r and theta l don't talk to each other, so they are basically commute, and the bosons of the left and right commute. So then the bosonic version of the field operator for right mover will actually commute with the bosonic version of the left mover rather than anti-commute. So it's clear, therefore, that there has to be an additional ingredient, and that additional ingredient is called the Klein factor. So that Klein factor can be defined in this fashion, etc. So he's done a lot of, he's just worked out lots of details, and you can see. So what I'm going to do is that I'm going to simply insert these files, because I'm not violating his copyright, I think, because his name is prominently displayed here. So I'm going to insert it into my PPT, and I'm going to circulate to all of you. And then it's going to be a complete account of, well, as complete as I can make it. Okay, it's definitely more complete than what you'll ever find in any literature, any book, any review article. But it can still be made a lot more complete. and that's for the readers to do. Okay, so I don't. So one of the reasons for giving this lecture is not for you to passively listen. I want you to also contribute. Okay, so I want you to sit down and fill all those nasty gaps, which are tedious and sometimes boring, but also important. Okay, so the gaps that are there, I want you to fill them in and send it to me so that I can again update this file and we can go from there. Okay, so the next lecture, the last lecture will be the next one where I will show how to calculate the single particle green function and density correlations using the diagonalized form of the interacting fermion theory. Okay, so that will be the last lecture. So I will use the bosonic form of the field operator, which is this one. Okay, so I'm going to show you how to use the bosonic form of the annihilation creation operator to calculate the single particle dynamical Green's function of the interacting theory. So that will be the last calculation. So that shows that uh, there are what are called Luttinger liquids. I won't actually discuss the physics of it. That will take too long. So basically, I will stop there once I get some mathematical expression for the single particle Green's function, and I'll tell you what Luttinger liquids are. And that will be the end of this lecture series. Okay. So this lecture series was only about the technical mathematical aspects of bosonization, which I was not fully convinced with. So I thank Professor Haldane for patiently explaining to me all those steps. And I also chastise the community for not explaining all these steps properly in the literature and pretending that it's all well understood when it's in fact not well understood. Okay, at least not only by me, I'm sure it's not well understood by people who think they understand it well. Because I'm old enough to know that. I've asked people pointed questions and they've given me vague answers, and I know that they know. I know that they don't know it and they're pretending to know it. Okay, so anyway, thanks for listening to me. I hope you will uh, spend effort looking into these details and filling in the gaps whenever you find them. Okay, so thank you. I'm stopping here. Are there any other questions? Any questions? No?
Mandira, do you have question?
No, I don't have any question. Actually, that is what I'm going to ask. There is anyone there want to ask any question? Okay, if not, then I think we can end this meeting here.
Yeah, and you tell me when should be my last lecture, and we'll finish there. It will take me maybe just 1 hour or slightly less. The next lecture
Oh,
I'll
okay,
finish.
maybe, sir, in next week, okay, we can
Yeah, okay, great.
have
Okay,
another.
please send me the recording of this lecture.
Yes, sure, sir. Sure.
Okay, wonderful. Thank you for listening.
Okay.
Bye bye.
Yeah.
Bye.
Thank you, all
Thank
of
you,
you.
sir. Thank you very much. Thank you.